Section 2.4, page 2. Let's go ahead and look at a couple more examples where the directions just say to differentiate. They don't tell me to use the product or quotient rule, but when I go to solve problem A, whose input variable is x, I see x in both the numerator and denominator of a function. So I need to think of that numerator as a standalone function whose derivative is just 1, right? This x turned into a 1 and the 6 was a 0. A standalone denominator function whose derivative is 3x squared plus 1. So as I go to take the derivative of k, using the formula derivative of the top, which we said was 1, times the original denominator. Ooh, this should be a minus. I don't have it as a minus here in the formula, but I do have it as a minus in my work. Now I need the derivative of the denominator, which I'd found off to the side, and I have the original numerator written next. And we write the denominator squared, and I mentioned before, but we didn't really need to see it. Always leave the denominator alone. Do not expand it even though it's squared. So in terms of left of my minus sign, 1 times anything is itself, so I don't need to worry about that. But this right side gets a little bit tricky. I've got 2 binomials that need to be multiplied, and then I'm subtracting the binomials all together. So what I have found is if people don't worry about the minus to begin with, and just focus on multiplying your binomials. So whether you're doing FOIL, distribution of box, but you're going to have to multiply the 3x with both terms, and then you're going to have to multiply the 1 with both terms. So I'm going to end up with these 4 terms, and in this case there is no like terms. Often multiplying binomials that will happen, but now I can go ahead and distribute that negative to get my negative in front of all of the signs. So I've left my denominator untouched, I've distributed my negative, and now when I go to look for like terms, I find a handful of like terms where I've written matching symbols above or below the terms, so you can understand where my numerator came from, but my denominator stays in its original untouched format. Generally, you're going to want to see if the numerator would cancel with the denominator, but because I've got the x cubed, x squared, and no x, which is not going to follow this pattern, there's definitely not going to be anything to cancel. Question B lets me know that my input value or variable is a t. I see a t under a radical, I see a t as part of a sign, and I think of them as being multiplied. So the square root of t I'm going to rewrite as t to the 1/2, so I can use the power rule. The sign of t doesn't need to be rewritten, but I am going to think of it as my other function. So in the beginning, I always like to find my derivatives of each part off to the side to save me some time. The derivative of the a function says start with your first function's derivative. So I'm going to go ahead and list that here. Multiplied by the second function's original format. Always plus with the product rule. The derivative of the second function. And then multiplied with the original first function. Again, there's really not much to clean up, other than I do have a negative exponent that I noted I'm going to bring down to the denominator. On the right side, other than we do tend to move variables out front of trigonometric functions, I'm going to go ahead and leave my answer this way. It is not one giant fraction, and you don't need to multiply this other piece by the 2t to the 1/2 times 2t to the 1/2 so that you can add terms. Just leave it as is. But now that you have these rules, there's a couple things to watch out for. Imagine I'm asked to take the derivative of 4/5x. Suddenly, this looks like a quotient rule problem to some people, and that will work. But if you remember, x only shows up once in the denominator, and I can rewrite that with the negative exponent to use the power rule that we'd already discussed. The key here really is that the denominator is a monomial, a single term, and we'll see that again in a minute. But if I took 4/5x and I decided to use a quotient rule, I would think of the numerator as a standalone function, but because it's a constant, its derivative is 0. The denominator is a standalone function whose derivative is 5. Now notice I had been talking before about numerator and denominator. I switched back to F and G notation because that's pretty standard for most textbooks and most tutors and Google and YouTube and whatever else you're looking at, but it still works the same. The formula says take the derivative of the top, which we said was 0, and so then I don't even really need to keep going where I take the original denominator, but I did. Always subtract the derivative of the denominator times the original numerator. And so really I have 0 minus 20, so we just need to write the 20, minus 20. When I write the denominator squared, because it is a monomial, I'm going to square the 5 to get 25, and I'm going to square the x to get x squared. Although this feels like my answer, I can simplify by dividing top and bottom by 5, and I get negative 4 over 5x squared. And really I should, have my y prime equals. But remember, we just said for this particular problem, why not move the x up front or just put it off to the side with a negative exponent? So I will leave 4/5 as a coefficient, bring my negative exponent out front, subtract 1 from the exponent, and as I multiply the negative 4/5, or the 4/5 with negative 1, and I take this denominator, or so the x squared to the denominator to fix the negative exponent, you notice that I have the same answer. Now, I mentioned up above, the key to this is that it's a monomial. The rule with splitting fractions, we only had one fraction there, is you can only split fractions if the addition or subtraction is up top, but not, absolutely not when it's in the denominator. So for example, if I have a plus b over c, as in this first example, I can think of it as 4 over the first term, and then 4 over the second term in the numerator. Because remember, once you have like denominators, you can add the numerators. But this allows me to think of this as 5/4 times the cosine of x and just 3/4. So that when I take a derivative, I have my coefficient of 5/4. The derivative of the cosine is negative the sine squared, and the derivative of a constant is 0. So I get my answer a lot easier than using a quotient rule. But if you have the reverse, and you have more than a monomial in the denominator, the only way to solve this is using the quotient rule. A standalone numerator, again, who happen to have a denominator of 0 because 4 is a constant, and a standalone denominator whose derivative is the negative 5 of sine x. So when I write my n prime, which we said was 0, and I multiply it times my original d, 0 times anything is 0, so that's gone. I need my subtraction. The derivative of the denominator and the numerator in its original form. I'm going to go ahead and multiply 4 with negative 5 to get negative 20, but we're subtracting that negative 20. So this is why we end up with a positive 20 sine of x, and I'm leaving my denominator as a binomial squared.